Question 4 states, evaluate limit as x approaches 0 of fx by using the cast to find sufficiently many terms in a Taylor series of the numerator and denominator. Yeah, so using the command Taylor and Maple are series in Mathematica, but in our case we'll just use Wolfram Alpha, just because the calculus book is a bit old, and yeah, so they probably didn't have access to Wolfram Alpha. And you just throw it in there and it'll just solve it for you. So we're going to basically use the same thing. We're going to find the limit by using Taylor series, or Taylor, Maclaurin, etc. So we're now asked to solve the limit using a cast to determine the Taylor series of the numerator and denominator. So using our trusty Wolfram Alpha calculator, we can determine the Taylor series centered at x equals 0, i.e. the Maclaurin series for both the numerator and denominator. So we just type in Taylor series of sine tan of x minus tan sine of x. We get this function. So you can just throw that into the Wolfram, and we'll throw this one, negative x to the power 7 minus 30, then minus 29x9 divided by 756, etc. Keeps going on. And also there's a plus o x to the 14. I'll get to that in a bit. And then if you do this for the denominator, we get Taylor series of a sine. You could just put a sine for arc sine, same thing as inverse, and automatically shows you this. A sine a tan of x, or inverse tan, and minus inverse tan of inverse sine of x. And then Taylor series expansion at x equals 0, that's just a Maclaurin. We get negative x to the 7 over 30. So it's similar to this one. So negative x divided by negative x to the 7 divided by 30. And then the next one's a bit different. So 29 is 756. The bottoms or the denominators are all the same. The tops are different except the first term. And then we get a plus 13x9 divided by 756, and then we have a minus, plus, minus. This is going to be alternating. There's also going to be a plus o x to the 14. Note that o is termed the quote big O notation and used to indicate that the series is a maximum absolute value beyond the evaluated term. So beyond this is going to be maximum of this order. And in our case, o x to the 14 indicates that the series sum of the remaining terms is a maximum value at has a maximum value of a constant multiplied by absolute value of x to the power 14. So in other words, that's the order of it. So whatever x is going to be a constant multiplied by whatever this x to the power 14 would be, when x is close to 0 in our case. So yeah, this is basically saying it's going to be maximum of this order, a constant times it by x to the power 14. Learn more, you can learn more at Wikipedia here with big O notation. Yeah, so I've not covered that earlier, but you don't need this. This is just to show a maximum or limiting factor of the series. So yes, infinite series is going to be at maximum this, and this one's going to be at maximum this one for this type of series that converges. Alright, so thus evaluating the limit of the Taylor series, we have, and I'm going to write this as limit as x approaches 0 of f of x, and then this equals to the limit as x approaches 0 of, again, the numerator n of x over the denominator d of x. And this is going to equal to, in a calculus book or the solution manual used equals to, and then put a cast just to show that we're skipping through a bunch of work and getting straight to the series. The limit as x approaches 0, and now we have over, and we're going to write the terms that all that matters is actually the first two terms, or the first term is all that matters, but we'll show you why everything else is going to vanish to 0. So negative x to the 7 divided by 30, let's do the first one. Negative x to the 7 divided by 30, and minus 29 x9 is 756. So this is going to be negative x to the 7 over 30, or actually better yet, just a bit easier to write, just put 1 over 30 like that, and then x to the 7, and then minus it's going to be 29 over 756 x to the 9. Then it goes minus dot dot dot, so that's all that matters. And the next one's going to be, remember the first term's the same, negative 1 over 30 x to the 7, and then minus, or this is going to be plus actually because it's alternating. It's going to be plus minus plus minus, so it's going to be 13 over 756, plus 13 over 756. It's going to be x to the 9. Yeah, this is x to the 9, 9, 11, then 13, etc. It's going to be, now it's going to be alternating, it's going to be negative plus dot dot dot. And now what I'll do now is I'm just going to multiply this top and bottom as per usual by the highest power, or the first power. I'm just going to do this by the 7 so that it gets rid of it, and then the other one's just going to be, well, x to the 2, and then it goes on and on, x to the 4, x 6, etc. So I'm going to go divide this by x to the 7 so we can cancel the first term, because that's all that matters. 1 over x to the 7, like that. So this means, well, this cancels with this, and those are going to cancel. So it's going to be, yeah, pretty obvious, so I'll just leave it like that. So this equals to limit as x approaches 0 of, now it's going to be a negative 1 over 30, because the x7's cancel. Now we're going to be 29 over 756. Now we're going to have x to the squared minus dot dot dot. Divide this by, yeah, let's move it here to divided by, and then the denominator, this one's also going to cancel, the x7. So 1 over 30, and then this can be x, x7 goes away. It's going to be plus 13 over 756 x squared. It's going to be minus plus dot, or minus plus the next one, plus dot dot dot. It's alternating. And yeah, now the later terms are all going to be, well, just 7 power to less, or the power, x to the 7 less. So it's going to be yeah, it's going to be 2, 4. So 11 minus 7 is 4, and then 13 is going to be 11. And those are all still going to be have an x value that's not x to the 0, which is 1. So in other words, when you plug in 0 inside all of these all just vanish. All you're left with is the first term. This one's cancels, so that's going to be 1 over 30. So then when you plug in the 0 inside here, this all goes to 0. Or not that part, but this part's going to go to 0. This part's going to go to 0. And then all the other ones are going to go to 0. Everything else is going to go to 0. This one's all going to go to 0. So all you're left with is negative 1 over 30 over negative 1 over 30. In other words, those cancel. This is equals to 1. Alright, so yeah, that equals to 1, which is the same as our question 3 that we solved using L'Hopital's rule. So this equals to 1, so we know the limit is 1. And now notice what we could do is, note that we could have also applied L'Hopital's rule to the Taylor series 7 times to obtain the same result as question 3. So we're going to just start from here. So instead of dividing by x to the 7 on both top and bottom, we're going to go, I'm just going to circle this and copy it. And then I'm going to move it here and paste. So let's say we start from here, and then we just take L'Hopital's rule instead of the series, of the power series, as opposed to of the other function using using Wolfram. Yeah, so just copy and paste that there. So now this equals 2, and I'll put a h for the derivative for L'Hopital's rule. So take the derivative of this one, of the top, this is a power rule, just put the 7 down and subtract the power. So this is going to equal to the limit as x approaches 0 of, now we get a negative 7 over 30. And then x6. And the next one's going to be, well, 29 over 756 times it by 9. And then we have a x to the 8, like that. So you just multiply the top power and then subtract it, dot, 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 and then divide this by the next one. This is 30. Don't know why that didn't copy. Okay, so now the 7 goes down, so negative 7 over 30, and then x to the 6 minus, I'm just going to be plus 13 times it by, well, 9, the same thing as before, 756, and then x to the 8 minus plus dot dot dot, and then do this 6 more times, because remember this 6, when you plug in 0 inside, these all go to 0 over 0, so again it goes to 0 over 0, so we do this 6 more times. So do this dot 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 6 more times. So the next one's going to be the 6 goes down there, and the next one's going to be 5, so 7 times 6 times 5 times 4 times 3. In other words, we get a factorial. So do this 6 more times, and then ultimately we get the last one, which is equals to this is the 7th one. So yeah, the first one plus 6 more is going to be x limit. L'Hopital's h equals 2 for L'Hopital's, like that, x to the 0, and then now we get a 7 factorial, which is again 7 times 6 times 5 etc. divided by 30. X to the x goes away. The next one's going to be number 6 more times, so this goes away. This is going to be x to the 2. This is going to be 29, and this is going to be 9 factorial over 2. This is going to be 9 times 2, 9 times all the way up to x to the 2. And this one here, this is just because 9 times 9 factorial over 2 factorial equals to, well, 9 times 8 times 7 times 6 times 5 times 4 times 3, because there's an x2, so we have to cancel all those. Divided by 2 times 1. So this is going to be 2 times 1. So it cancels all those. So we're left with, just the, we have to cancel that. Oh, that's why we have a 2 factorial at the bottom. Divide this by negative 7 factorial, and then x to the 0 or 1. And then, like that, it's going to be minus dot dot dot. And also put this 756. Now the next one's going to be plus 13 over 756 times it by exactly the same thing. 9 factorial over 2 factorial. This is going to be x2, and it keeps going on and on. Then minus plus is alternating dot dot dot. And then when you plug in the 0, this goes to 0. Everything else goes to 0. This goes to 0. This goes to 0. So all we're left with is this over there. This equals to, this equals to negative 7 factorial over 30. Divide this by, I'll put this a bit neater. Let's put it over here at the bottom here. So this equals to 7 factorial over 30 divided by 7 factorial over 30. And in fact, when you calculate this out, this equals to, this equals to negative 168 over 168. So this is exactly what we get. So circle this out like that. Don't circle that until we get the answers. This equals to 1. And this is exactly the same thing as our solution, or our question 3. So if you calculation check, you go 7 factorial equals 5040, and you get negative 7 factorial divided by 30, we get this negative 168. So that's exactly this. So this result agrees with the result in question 3, which had the exact same one. So anyways, now let's look at question 5. So let's go read it. Question 5 states, use the limit command on your cast to find the limit as x approaches 0 of f(x) directly, and most computer algebra systems use the method of question 4 to compute limits. So yeah, most of them just use Taylor series and all of a sudden just take the limit, because it's pretty epic stuff. Because Taylor series just makes any random calculation, like for example sine, trigonometric ones, inverse functions, all into basic polynomials where you're just adding infinite terms of x to the power of something and then times a constant. So you make these all uniform and calculate it, which is quite amazing if you start to ponder it. So anyways, let's go to question 5, and you could again use amazing Wolfram Alpha. Just calculate that. So let's go to Wolfram Alpha, and it's a solution to question 5. So if we calculate, if we calculate the limit directly using Wolfram Alpha, we get the correct answer. There's a link to it. So you could just literally just type limit of sine tan of x minus tan sine of x divided by a sine, or for inverse, a sine a tan of x minus a tan a tan of a sine of x, all brackets. Get the brackets all correct. As x approaches 0, you get limit as x approaches 0, and it automatically shows you in this format. Sine tan of x minus tan sine of x, etc. Inverse sine of inverse tan of x minus inverse tan of inverse sine of x, all brackets, equals 1. Fascinating stuff.